Hi class. This week we will complete our model for mechanics by expanding what we have seen thus far to cover rotational motion. So as a reminder, let's look at the differences in between translational motion and rotational motion. So for translational motion, it means that you have some sort of mass m, and this mass is allowed to move translationally, which means that it can move in a straight line up or down, or has some mix of motion up or down in any direction. And the thing to note here is that for all intents and purposes, as long as your motion is entirely translational, it means that you can treat this this body as a point mass, in which all of the mass is located at one point, and that the motion is directly attached to that point. And this is the premise in when we build free body diagrams and look at forces. All right, so let's compare this to rotational motion that we have seen a few weeks prior. Let's see, so rotational motion. Rotational motion is different in the sense that, let's say you have a mass, a body, mass m, and if you allow this body to undergo rotations, the first thing that you must define is the axis of rotation, which means that, let's say we'll put an X here. That means that this body is allowed to rotate around that point. And we'll decide on some convention directions, meaning that if the body rotates, so let's say that if the body rotates this way, we'll call that rotation positive, and if the body rotates this way, the body rotates negative. The rotation is negative. And you can imagine that I can pick any point in this object to rotate it about and describe such a rotation. So I could choose this point and allowing this body to rotate around that point. And the point of rotation does not need to be inside the body either. So we could potentially have a point of rotation right here in which this entire body sort of orbits around this thing in some way. The thing to note here is that you can no longer treat this as a point mass. You have to treat this as an extended object. So point mass here does not work. Okay. So we have already starting to see back in kinematics how to take translational motion and turn it into rotational motion. So let me write out the equations for translation. So if you have translational motion, the kinematics for translation, which means the description of motion, can be encapsulated into two equations. So x, this is the displacement, is equals to 1/2 linear acceleration times squared plus velocity initial time plus initial position. And the other one is that velocity final equals to the linear acceleration times time plus velocity initial. So we discussed in class that that for these two equations is all you need for kinematics. As in, if you know the acceleration, then the motion, the linear acceleration, and the initial conditions, as in the initial velocities and initial positions, then the motion is completely defined up to any amount of coordinates you have, from 1 coordinate problems to 3 coordinate problems. This is all you need to describe motion. However, if the problem is, if the object is also allowed to translate, this cannot tackle that additional degree of freedom. So what we do is this: if we send, and this is just a review, we already done this in class, but if you send, let me do up here. So if you send x to an angle coordinate, velocity to an angular velocity, and linear acceleration to an angular acceleration, and you translate these terms according to this, you will find the set of equations that are appropriate to use when an object is allowed to rotate. That is, some angular position final is 1/2 angular acceleration time squared plus initial angular speed times time plus the initial angular position, and the final angular speed equals to the angular acceleration times time plus the angular speed initial. Okay, so this covers all of kinematics. As in, if you're only interested in describing the motion, either it be if your body can only translate, or if your body can translate and rotate, these 4 equations is all you need. Okay, so that's true for kinematics. But you might be wondering, can we extend this from kinematics to the entire model of physics we've built so far? And the first thing I want to bring your attention to is forces. So we said after kinematics, our first model for why motion happens was the invention of something called force equals to mass times acceleration. Okay, so what does it mean? This means that Newton's second law, you have, or Newton's first law, you have inertia. So you have your inertial term right here. So this is an inertial term, meaning that what causes acceleration is what causes the motion to change. In mass is what resists the motion from being changed in any way, and we will call whatever changes the state of motion of an object a force F. Now, let's note that this acceleration here is a linear acceleration. It's a translational acceleration, meaning that a force can only affect a force will affect an object if applied at in this object to change the translational motion. Okay. All right. So now, can we come up with an analog for rotational motion? The answer is yes, meaning that if you have a state of translational motion, you apply a force to change it. Now, if you have a state of rotational motion, you must now apply a new quantity to change its rotational motion state. First thing we need to do here is we need to introduce a concept of rotational inertia, right? So here mass is what, so here mass is the term that is responsible to carry the idea of inertia into this equation. For rotational motion, we'll call this the moment of inertia. It's devised by a letter I, but it will do the same job. So it will cause the object to resist change in its rotational motion. So far we have I, and now we have acceleration. We already decided that goes to angular acceleration, right there. And the new term we're going to call torque. And I think that some of you already have some sort of experience with this term right here. So what happens here is, again, I is an inertial term. And force is what changes the motion of an object in a translational way. And torque is what changes the rotational state of motion of an object. So either this way or that way. Okay? And linear acceleration and angular acceleration, we already spoke about this. Which means that to extend the idea of forces to a rotational analog, you send a force to a torque. Okay, so this comes in really useful whenever your bodies are allowed to rotate. And another a quick remark I want to make about this one is that this one is a little harder to imagine as far as torque and forces is concerned. But if you imagine trying to twist something, if something twists very easily, that means that the inertial term here is very low. In the same way that if you push something and that something changes, it gives away right away, then its mass is very low, and you all have some sort of intuition with that. But if you try to twist something and it's very difficult, then that means that this inertial term here is very high. So mass, you all understand because mass is something that you can put on a scale. Gravitational mass is the same as inertial mass. And that's enough to sort of help with your intuition. However, this moment of inertia here is not something that you can put on a scale. And let me make another point here. Do you see this object here with mass m? And I have 3 points of rotation, and you can rotate any object according to any point of rotation. Now, the moment of inertia of this object that's being rotated here is not the same as the moment of inertia of this object being rotated around here, and it's probably also different than the moment of inertia of the point being rotated around here. Which means that if you don't know at what point you are rotating about, there's no way for you to know what moment of inertia for any object is, which is very different than mass. Mass, it does not matter what the object shape is like. It does not matter where you hold the object. Mass is always mass. It's, like I said, you put it on a scale, it's done. Moment of inertia, however, is different depending on the point of rotation. Okay. Now, the obvious follow-up question here is there are more things we did in this class as far as translational motion. And I wanted to bring your attention to two things. One was we also constructed momentum. So momentum was equals to mass times velocity. And again, this was an amount of motion, an amount of translational motion. And that motion, and this here was conserved, remember? Now, I will make the argument that there is also an amount of rotational motion. So we'll note that by L, and this is M again, is the inertial term for rotation is moment of inertia. So that makes it in here in the same way that mass. And in velocity, linear velocity gets translated to angular velocity, right? So in this case, linear momentum gets sent to angular momentum, meaning linear momentum is an amount of translational motion, and angular momentum is an amount of rotational motion, which is proportional to the inertia term multiplied by translational velocity and versus rotational velocity. And the last thing I want to write here is kinetic energy. Is 1/2 mass times velocity squared. This was an amount of motion, an amount of energy that is tied to translational motion. There is also a kinetic energy that's amount to rotational motion. Mass here is just an inertial term. Every inertial term is denoted by the moment of inertia for rotational motion, I. And this is a speed squared, linear speed squared, which means that you need to put an angular speed squared over here. Now, I want to make a quick note about these, is that force and torque, they're analogs, as in you can never set a force. Force is the units of force are different than the units of torque. The same way that units of velocity are different than the units of angular velocity, and the units of displacement are different than the units of the angle you use. Okay, and the units of momentum are also very different than the units of angular momentum. This is why they're denoted by different letters. Now, this is where kinetic energy is special here. These here are the same. They are energy. So 1/2 mv squared, you already know that this works out to be joules. This also is a kinetic energy. So we denote this as the rotational kinetic energy. This is the only time in which you will in one equation mix these two, because they have the same units, which means that for an object that can rotate, so let's say you had a disk. There's a line here to mark where the disk is disk is pointing. If this disk has a velocity v that's translational, but there's enough friction here to get this thing rolling this way with angular speed, then the total kinetic energy here will be the sum of the translational kinetic energy right there plus the rotational energy. Okay? So these two are very special because they will show up in the same equations. They are an energy concept. They are the same. They're the same unit. But everything else here, right here, everything else, this column, the translational, the kinematics, the description of translational motion, and the model for translational motion is different than the description of angular motion and the model of rotational motion. Okay, so the remainder of the course we will finish mechanics. So what you're looking right here is basically every equation we've gone through so far, this in the semester more or less, organized in a way that tells you if your body only translates, you only have to worry about this on the left. If your body also rotates, you have to worry about these on the right. And what we are going to cover on the next videos to finish off mechanics is um, we'll start with torque and what that means for an equilibrium of an object. Then we'll quickly do conservation of angular momentum, which is the third conservation law. And if time allows, I will also include some simple rotational kinetic energy problems. And this will be more or less a review of conservation of energy with the added kinetic energies in here. All right, have a very good day, and I'll talk to you all soon.